Okay, hello, my name is Delaney Elliott, and this is my presentation on high-dimensional photon entanglement using multiple silicon ring resonators. So the first thing I want to talk about is what an integrated photonic is. It's essentially in our case, a silicon chip um, that is similar to something like an integrated electronic, such as a CPU that you'd have in your computer or other electronics, other electronic ICs. But instead, it's optical. So the paths are waveguides, which are similar to fiber optics, and things are controlled using heaters that change the refractive index of the silicon waveguides and allow us to perform operations on our light. So it allows for more scalable, accessible, and scalable optical experiments. Some experiments that would normally be confined to an entire table benchtop experiment is able to be shrunk down to a chip that's less than an inch squared. Um, and it also provides easier integration with other components. So we have heaters that change the refractive index instead of having to physically change the position of something in free space. And we also have things such as photodiodes to take measurements within our chip, which is very helpful for doing research. So specifically my project for the summer and moving into my capstone, because we anticipate this project to be about a year-long project, is to create and measure high-dimensional entanglement with something we call a QDIT chip, which the layout of that is in the top right corner. It basically consists of 8 silicon microring resonators that are in parallel. And microring resonators are important because they create entangled particles due to something called spontaneous four-wave mixing, which essentially allows them to take in 2 photons and release 2 photons with the same energy but different wavelengths that are effectively entangled. So my summer goals were to prepare the chip and the setup for the experiment, start learning to use the equipment needed to control and test the chip, and then begin controlling the chip and characterize the electrical and optical components of the chip. Also, to the final goal, which we haven't reached yet, is to measure photon correlations of the entangled photon pairs. So the first part of this this project was packaging. Uh, our tiny chip, as you can see in the image in the center, was shimmed using an aluminum oxide substrate and then die bonded to something we call a fan out board, which basically just fans out electrical connections. That's the gold board that you see in this image here. And then those electrical connections were wire bonded to a PCB board that allowed us to interface with the chip using a ribbon cable. These wires are, I believe, 14 microns in diameter, so they're very tiny and very fragile, and they have to be placed with essentially a robotic arm, which I had to learn how to use. So once we had the chip packaged, it was time to create a setup. Luckily, somebody had just been finishing their experiment, and I was able to repurpose their setup. But I had to make some augmentations, such as using a different laser, as well as creating a holding mount for our chip and a covering for our chip, as well as holding things to hold our fibers. So both the input fiber and the output fiber array are on 6-axis stages, which gives us a lot of control over where the fiber is and the coupling of these devices to the chip. And we have a microscope that has visible and IR cameras connected to it. I originally didn't think we needed the IR camera, but it has been a lifesaver, and it also has produced some cool images, as you'll see later. So we were able to take real-time light measurements, which allowed us to couple the fiber with basically a feedback loop. We could make an adjustment on our stages and then see how it changed our transmission through the chip and kind of couple that way. So uh, once we had the setup made, it was time for classical optical characterization of the chip, the components on the chip. Um, I had to connect the laser to a high-speed voltage analog to digital converter, which is able to get rapid measurements. I think we got about 5,000 per second of the output wavelength because our laser essentially only had a voltage output that was proportional to the wavelength, and that allowed us to take high resolution, fairly quick sweeps, which made the process of collecting data much easier than it would have been had we not had this device. Um, and we were able to use these sweeps to characterize the rings and find out the resonances. Another cool kind of video down here is us sweeping through some wavelengths, and we can see the ring in the center uh, becoming in resonance at a certain wavelength as it glows. And then we also can see a Mach-Zehnder lobe that is connected to the ring coming into resonance at a different time. So what you're seeing here is basically this circuit here, but we get to see it using an IR camera and actual light running through it. So running those sweeps, we can get a plot similar to this, which we see these troughs, which are when the ring is in resonance and would be producing photon pairs. We can see around here that there aren't troughs such as where we would see them in between the other troughs. And that's because the Mach-Zehnder interferometer that was connected to the ring is actually not allowing coupling at those wavelengths. It's just, yeah. So once we had the ring sweeps, it was time for electrical control. So the board had 52 electrical connections, including Mach-Zehnder interferometers, ring resonators, and photodiodes. We used a device called a control QI or Q8IV, which was able to control the connections. And we also tested a chip called an analog devices LTC2662, but that's still in development, so we're not using that yet. This is an image produced by one of my colleagues, Eric Russo. It basically shows the electrical connections, and we can see, for example, things that aren't parallel along the y equals x line, such as these, are photodiodes because they're polarity specific. So this was a really good way for us to test if our chip is working, if all of our wire bonds are effective, and make sure we don't have any shorts or anything. So once we had control of the electronics, we were able to start characterizing the electronic components. So here we see, here we increased the voltage of the Mach-Zehnder interferometers, and we saw how the resonance has changed. So the first thing we notice is as the voltage increased, the resonance of the ring increased, which indicated that there's thermal crosstalk between the Mach-Zehnder interferometer and the ring resonator, which is important to know in the future when we need to tune the ring resonators to a specific resonance. We also see that the peaks decrease as we increase voltage, which indicates that the coupling is being decreased as the Mach-Zehnder resonance changes. We also characterized phase shifters, which allow us to direct the light into specific rings just for measurement purposes and for ensuring that we have an equal distribution of light to every ring when we need it for our quantum characterizations. So this is basically a plot of how power changes the light transmission through a certain ring. So we see basically we're able to increase the light going through a ring by about 3 dBm, which is it's expected because that's about a double in light, measured light, which is what would be expected for a binary split. We also are able to characterize the second phase shifter. We weren't able to get as much of an increase in power using this, but we start to see kind of the sinusoidal shape that this should take as the light goes through a full phase. These gaps you see here are basically due to our so little light going through the circuit that our photodetectors aren't able to measure it. So with all that being done, uh, we're looking to continue to gain better control of the chip using better coupling, or by creating better coupling using the MZIs, the Mach-Zehnder interferometers, and we also want to be able to control the resonances and the Mach-Zehnder interferometer simultaneously. So that comes down to managing that thermal crosstalk that we saw in that previous plot. Once we have control of that, we have enough control of the chip to verify position correlations of photon pairs, which consists of measuring individual photons and determining if photon pairs are produced at individual rings, and make sure that we aren't getting photons at different rings being created at the same time. And then after that, likely during capstone, we'll begin measuring the momentum correlations, and the combination of the momentum and position correlations uh, show us that we have high dimensional entanglement, and we essentially have a QDIT chip, which is a higher dimensional bit, basically, for potentially quantum computing. So lastly, I'd like to thank my advisor, Dr. Howland. I'd also like to thank Dr. Preble and some of my colleagues, Eric Russo and Evan Manfreda. And I'd like to thank all of the RIT Integrated Photonics group. Everybody's been great, and I've learned a lot from this summer research. And if you have any questions, please contact me at jde6925@rit.edu. Thank you.